Yes, thank you. I'm going to share my screen. 1 second. Okay, can you see my screen?
Yes, we can see it.
Okay, so I will not go to full screen because we tried earlier and there were obvious problems with the share part. So I'll use this window. Hopefully everyone can see what I'm presenting.
You can see it very well. So
Thank
you can
you.
start what you like.
Thank you. So thank you very much for the invitation, and thank you to the organizers for letting me have a chance to speak at this conference, which I've been enjoying for the past. I've been able to follow. Today I want to introduce some considerations on what we need to be aware of when we deal with dust, especially in the era of petabyte size surveys. A brief summary slide of what we can expect about the effects of dust on stellar populations. Let's remember that whenever we conduct measurements, usually we observe galaxies or stars or other subsets of emitters. And in the electromagnetic bands that we usually target, dust plays an important role. How am I describing this? Is spectral energy distribution as a function of wavelength going from the X-rays all the way to the far infrared of two stellar populations. These are models for simplicity. The blue one is a stellar population in the absence of dust, and the red line outline is a stellar population with dust, so it's a dusty stellar population. And of course, we are familiar with the effects. There is a global dimming of the UV and optical and near-infrared light, and there is the appearance of mid and far infrared light, which we call generally dust emission. And ionizing photons usually are actually not seen because it's a combination of absorption by gas and absorption by dust. But we will not specifically deal with ionizing photons because they actually go through a number of processes that are far more complex. So I will concentrate on rest frame, UV optical, and near IR for my discussion. The impact of dust is remarkable also when we talk about cosmology, and this is perhaps of more interest to the audience in this conference. As an example, I'll bring the ESA mission Euclid, which is expected to be launched around the end of 2022. And the stated goal of the ESA mission is to constrain dark energy and dark matter. Their general word for this is constrain the geometry of the universe using two main tools: weak gravitational lensing, which I will indicate as WL, and baryonic acoustic oscillation, standardly referred to as BAO. The weak gravitational lensing generally probes gravitational effects from its own by definition, and can constrain the geometry of the universe from the ratio of distances of the target sources. The top figure to the right shows a picture that I lifted from the European Space Agency website that shows the difference in the shape of a galaxy from no lensing to weak lensing all the way to strong lensing. We're much more familiar with strong lensing than weak lensing, but weak lensing alters the shape of galaxies. A single galaxy will not provide you much information, but a collection of many thousands of galaxies can constrain the gravitational effects of the lens. Now, what weak lenses requires is the recovery of galaxy shapes and accurate distances of the lens and the lensed objects. Weak lensing is achromatic, but the recovered shapes of galaxies do depend on the presence of dust. And so they're extremely sensitive to the effects of dust attenuation. In addition, distances for the majority of the Euclid targets, for more than 99% of the Euclid targets, will be recovered through so-called photometric redshift. So you will not have a spectroscope with emission lines that can uniquely identify the redshift of the galaxy. you will actually have to rely on modeling of the spectral energy distribution of the sources from sparse photometry. That adds a layer of complication because dust attenuation becomes a major issue, especially for the redshift range chosen by Euclid, which is around redshift 2. A similar argument can be brought forward for baryonic acoustic oscillations, which of course probe the geometry of the universe and its evolution, but they also require accurate distances because practically what baryonic acoustic oscillations provide is the standard rod. So like above, distances become crucial and the presence of dust can affect in rather significant ways the measurements of absolute distances. Now, the worry about dust is because in order for Euclid to be successful, the requirements on success in recovering intrinsic distances from photometric redshifts are quite exacting, meaning that they need a 3% overall accuracy with a less than 5% catastrophic failures, which is a much higher level of accuracy than ever required before. There are also far more, allow me to say the word, mundane effects of dust on galaxy evolution, on our understanding of galaxy evolution. Dust, just to be clear, doesn't affect galaxy evolution in any particular way beyond favoring or disfavoring star formation, but does affect in a rather measurable ways how we quantify galaxy evolution. So on the top left is a plot showing the star formation rate density per unit moving volume as a function of redshift of star formation in galaxies. Each slice of redshift represents a large sample of galaxies at that redshift, probed at two wavelengths. One is extreme ultraviolet, which traditionally probes massive stars and therefore should be probing a massive star formation. And the red dots are at infrared wavelengths, which traditionally probe a star formation that is hidden by dust from direct view. So it's UV light absorbed by dust and re-emitted in the infrared. And you can already see that around the redshift 2, there is between redshift 1 and 2, there is a peak in the infrared, and it's actually the infrared is 3 to 5 times higher than the extreme ultraviolet. Now, the top right shows a heroic effort by two authors, Maddow and Dickinson, to bring these two measurements, these two rather contrasting measurements into agreement with each other and provide a coherent view of the evolution of the cosmic star formation rate density as a function of redshift. But let's not forget that this heroic effort actually requires assumptions. Now, why do we worry about dust and why do we have such a predominant amount of dust or dust effects at high redshift? We would expect that the higher the redshift, the lower the metallicity of the galaxy, the lower its overall dust. This is only partially accurate because galaxies, as you go back in redshift, the galaxies correctly decrease in overall metallicity, but they also increase in the overall gas amount, gas fraction. And there is a sweet spot. So if you go to an extremely high redshift, you have a lot of dust, but a lot of gas, but the amount of metallicity is so low that it really doesn't really enter into the picture very much. Although this is still a question mark, as you can see from the top left plot. But as you decrease in redshift, so you come closer to our times, you decrease the overall amount of gas and increase the metallicity, and you reach a sweet spot at between redshift 1 and 3, in which the effects of dust are maximized on galaxies. So this is not very much appreciated. A lot of our colleagues think that most of the dust effects are visible in the local universe. In reality, most of the dust effects are present between redshift 1 and 3. So the overall impact can translate into errors of a factor between 2 and 10 on star formation rates when you measure them from observations, and between a 20% and a factor 3 on stellar mass estimates. Why do we need accurate cosmic star formation rates? Well, first of all, none of us would think that an uncertainty of a factor 2 to 10 is acceptable. But beyond the aesthetic pleasure of having an accurate measurement, there is actually an important consequence. Many models of galaxy evolution predict roughly the same trends as shown in this picture taken from a paper by Suresh et al. 2015, in which you can see that for the accuracy of the time 5 years ago, which is not very different from the accuracy we have today, many models for galaxy evolution actually fit the data. So you need really to restrict and constrain the star formation rate density and its evolution across cosmic times to a much higher level of accuracy in order to discriminate between these many models. At this moment, only the higher mass loading model is somewhat rejected, but not even that strongly. Another impact of dust is at the time of reionization. Again, why do we worry about dust at redshift 6 or 9? Dust enrichment in galaxies, although we still know very little, appears to be happening very quickly. So if galaxies start producing stars at redshift 15 or 20, by redshift 9-6, during the full reionization of the universe, effects of dust might actually alter our ability to explain how reionization occurred. The added complication is that at those redshifts, we cannot really probe ionizing photon leakage because of the opacity of the IgM. So we need to use indirect probes to measure how many ionizing photons are actually leaking out of galaxies. The current dilemma is between whether stellar populations produce the reionization, and in particular low mass galaxies, versus the early black holes that formed at those times, and how and what is the relevant impact of each other and how they relate to each other is still a question mark. However, it's pretty clear that under standard conditions of star formation, you need to remove dust, the cocoon of dust, from regions of star formation within the first 2 or 3 million years in order to provide a significant gas ionizing photon leakage through standard channels that are formed in the interstellar medium, and from there out of the galaxy. So geometry in this case becomes key. In order to appreciate why geometry is key, I have prepared a cartoon of the same stellar population and the same layer of dust, but two different geometries. In the top geometry, the dust and the stars are homogeneously mixed together. These are just toys, okay, toy models. In the second example, the dust is the same amount of dust, the same thickness, but in front of all the stars. So it's positioned in front of all the stars. On the right-hand side, you see in both cases the input population as a function, so it's the luminosity as a function of wavelength from the UV to the near IR. So I'm just showing from about 1,000 angstrom to about 20,000 angstroms, 2 microns. And you can see that the input population is identical. EB minus V is the thickness of the dust layer, and it's 0.5 for each of them. This is a color excess, is related to the thickness of the dust layer. But the output spectra, which are in red, are dramatically different. So geometry becomes a key factor in determining how much of the stellar population we can actually observe and how we can hope to recover it. Now, galaxies are even far more complex than the two toy models I just showed earlier, a few seconds ago. Dust is not homogeneously distributed. Stars can occupy locations that can be in front, in between, in the middle, behind any cloud of dust and gas in their own galaxy. So the effects are multiple and varied. And one of the earliest papers that made very clever observations about the problem was the one by Wittronson and Capuano in 1992, when the authors observed that astronomers tend to adopt the so-called mythical overlying screen of dust, which of course is a non-existent mythology when you start to deal with real galaxies. Amid all this complexity, how do we proceed? Well, first of all, and this is again, I'm recalling the first slide of the spectral energy distribution of a stellar population with and without dust. There are a few trends that one can observe. First trend, which seems to be fairly systematic in many environments, is that as you increase the amount of dust, the slope of the UV continuum, the one that I'm calling beta or UV slope, and is marked by the two arrows here, the UV slope becomes less negative, or if you will, redder, okay? And as it becomes redder, it also decreases in intensity, while at the same time, the far infrared beyond 10 micron increases in luminosity. So the ratio between the total infrared and the intensity in the UV, the measured intensity in the UV, is telling you how much dust you are dealing with, while the shape of the UV slope, the value of the UV slope, as it becomes redder and redder, tells you how much selective attenuation you have, how that affects your spectral energy distribution as a function of wavelength. If you plot these two quantities together, so the ratio of the infrared to the UV luminosity versus the measured UV slope in local starburst galaxies, you find a very clear relation. I hope you can all see this plot. It's now traditionally called the IRX beta relation, where IRX stands for infrared excess, and beta is the UV slope, or the some UV color that probes the same type of measurement. So as you can see, nearby galaxies, and that was actually found about 25 or 26 years ago for the first time, and then reiterated in several subsequent papers. Local starburst galaxies seem to be following a rather narrow sequence, at least narrow when you talk about galaxies, is about a factor 2 spread, and that's what you're seeing here, around a very narrow sequence of increasing, reddening UV slope for increasing IRX value. That was codified by the authors into what is now called the Starburst attenuation curve, which is represented to the little plot on the right in blue, compared with extinction curves of local galaxies. So the extinctions that you find when measuring individual stars. So starburst galaxies are affected by dust in a slightly different way from, well, slightly when you look at the numbers, but in significant ways, because all these values are multiplied to the power of 10, so they're taken to the power of 10. From starburst galaxies are different from individual stars. Now, that nice, clean correlation only lasted a few years as researchers continue to investigate different galaxies, so not just starburst, but also other galaxies with a more varied morphologies and more varied star formation histories. They started to realize that that single relationship didn't seem to be enough to explain every galaxy. You had a huge variety, and these are simplified by this collection of plots. It's a messy slide, but it's simply for the purpose of communicating that the single relation that was found in 1994, already in the early 2000s, was no longer that unique. It was not that tight, and the galaxies seem to be occupying a much broader swath of the IRX beta plane. And in particular, it was immediately noticed that the so-called normal star-forming galaxies, which I will define in a second, do not behave like starburst galaxies. Now, normal star-forming galaxies usually have star formation rate densities, surface densities that are about 10 to 1,000 times lower than starburst. So their density of surface density of star formation is several orders of magnitude lower. and they have a much more varied, typically they have more varied morphologies. I'm showing M51 as an example of a normal star-forming galaxy, while starburst galaxies, at least in the local universe, tend to be centrally concentrated blob of coherent star formation, like NGC 5253, which is the galaxy shown at the bottom right of the slide. Okay, what happens then at high redshift? High redshift also yielded its a mixed bag of successes and puzzles. So some of the very first papers by Naveen Reddy and collaborators, this is the plot to the top left of the slide, show that starburst galaxies, which are the ones marked in blue, with the star formation histories longer than about 100 million years at redshift 2 to 3, seem to be following the standard starburst curve. Oh, that was great.
5 minutes left, Daniela.
Thank you. Okay, then you moved, however, to include a more complex samples of galaxies, and that revealed again, as the two plots to the right show, the one at the top and the one at the bottom, that not all galaxies seem to fall onto the standard starburst attenuation curve. Now, many authors tried to understand what was happening, maybe different galaxies, different types of attenuation curves, maybe different normalizations. Some actually started to look at the complexity of stellar populations once you move from a centrally concentrated starburst with a lot of unique and single stellar population with far more complex star formation histories in which some areas of the galaxy might ignite the star formation earlier than others. You are collecting a lot of stars over the Hubble time. Therefore, the complexity of the star formation history might play a role. And again, this is a very busy slide, and its only goal is to show that authors tried to use multiple stellar population to try to explain the variety of behaviors on the IRX beta plot. However, one of the problems is that the correlation does not prove causation, in the sense that, yes, they are consistent, but we can actually uniquely prove that a star formation history plays a major role in these effects. So my team looked at the star formation history of a galaxy, nearby galaxy, and trying to model it in detail. Now, you might think this is to be a little busy work, but unless you can prove definitely that the star formation history has an effect on the position of a galaxy on the IRX beta plot, you are back to square one of many potentially degenerate hypotheses, including variations of the attenuation curve. So we went on and started to model individual regions in this nearby starburst galaxy, NGC 3351. In the plot to the right, you can see its location on the RX beta diagram. So the region called the SB center, which is the center of this galaxy, and also the galaxy itself, they are located far removed from the starburst curve, which is marked by the continuous black line on the right plot. We reconstructed the entire star formation history of this galaxy, and it's actually plotted at the bottom left. That's the star formation rate as a function of age, and you can definitely tell that the size of the bars marks the uncertainty, and the different colors mark different regions in age, in duration. And you can definitely tell that this galaxy had everything except either instantaneous burst population or continuous star formation. Is actually as a sort of U-shaped star formation history. Once you include that in your modeling, you can reconstruct the position of the starburst center and or close to the position of the galaxy with the continuous line with a dash hatched area. So again, star formation history has an outsized impact on the location of a galaxy on the RX beta diagram. Why am I remarking so much this plot? this plot is extremely important because the slope, the UV slope, is extremely easy to measure at all distances. Even JWST will be able to measure UV slopes of galaxies redshift 10, while the infrared excess is unmeasurable by most, even with ALMA, even with some of the deepest ALMA observations, except for a few objects. And so what happens is that by using a very simple tool, like a measurement of a spectral slope, you can recover the intrinsic flux of a galaxy in the UV and the infrared, and therefore recover its star formation rate. So moving to my conclusions, the effects of dust and the removal are key for quantifying the evolution of galaxy and constraining the geometry of the dark universe. Establishing cheap methods, by cheap meaning something that is easy to measure but has a big return in terms of recovering intrinsic quantities of galaxies like the star formation rate. So the ratio of the IRX is a ratio of the infrared to UV. By measuring the luminosity in the UV, you can recover the total infrared and therefore also it's the star formation rate of the galaxy with a relatively high accuracy. That the establishing cheap methods will increase in importance with petabyte surveys. Let's think about the LSST and other many upcoming huge surveys. The original cheap method, the IRX beta relation, works well for starburst galaxies, but has turned out to have a large scatter when less active galaxies are included. Suggestions that have been explored are variations in that attenuation shape, its normalization and dependency on the star formation history. And we have proven through a careful analysis of one active galaxy in the near universe that actually it is star formation history that has the lion's share in determining the location of a galaxy in the IRX beta relation. Thank you.
Thank you, Daniela, for your presentation. Now there is time for questions. If there is any, let's see if someone writes something in the chat. So far, there are no questions. In the meantime, I would like to ask you something. It is a precision measurement of the dust. Of course, as you mentioned and you show us very well, it is key point for the evolution of the galaxy. So. My question is if there has been already shown any tension with cosmological model.
Sorry, the dust has shown tension with the cosmological models?
Yes. In terms of what you expect from the evolution of the galaxy. Yes,
so there are many tensions. I'm not sure which one you are referring to. But sorry?
Any.
Oh, okay. So tensions are in reality in the assumptions that are made to reconcile measurements. So when you're trying to reconcile, for instance, when you're trying to reconcile the infrared measurements and the UV measurements of galaxies at redshift 2, you're making assumptions on what you believe are the underlying stellar populations and the dust properties of those galaxies. The results are all over the map when people actually go in the surveys and perform actual measurements. And the problem is that there are enough degeneracies at this point that you can practically hide a lot of problems under the carpet. So the problem is not so much that you cannot explain results, is that you have enough degeneracies that you don't know if your results are correct.
Okay, I understand. Thank you. Is there any question? I don't see more questions here in the chat.
If I may ask the question, Daniela, it's Gregory. Just a curiosity, you mentioned this U-shape of the star formation in particular galaxy. Is this typical? I mean, we are accustomed to the inverse U-shape, let's say. What could be the physical reason for this U-shape? What do you think?
That's an excellent question. So this is actually a region that is known, first of all, recent accretion of dust because, of gas, because it's a bar. And the bar is probably become active about 100 million years ago. Previous to that, the accumulation of gas might be enhanced by the bar itself. So there has been a lull, presumably in the accretion of gas in the region over the past, say, 50 to 300 or 400 million years. We're still investigating the issue, but there is a bar. So the bar, feeding of the center by the bar might have a role in this result.
Okay, thank you.
Daniela, if I, first of all, beautiful talk, congratulations. We are very interested in these days, of course, in GRBs. And we are observing GRB at Z of the order of 9, for example, 0904 29b.
Mm-hmm.
How would you, this GRB have necessarily to be created by the interaction of a supernova accreting on a neutron star already formed? How can you see how to form such an evolved system in your picture in some of the early galaxy at so early stage? If you have any possible input.
I don't know if I have an input that wouldn't be already in the literature. So the formation of the seeds of black holes is still a highly debated field as far as I know. And I don't know if we really have a clear picture of when the earliest black holes and compact objects have formed. They could have formed much earlier than we think. One of the big surprises for most astronomers is to find fully formed, heavily dust enshrouded AGNs already at redshift 7 or 8. And you wouldn't expect that. The universe is too young to have that.
Exactly. And even more, if you have a GRB with a black hole and a neutron star at Z=9.
The issue, fundamental issue, is that as of today, we have no clear picture of dust formation and evolution. So once dust is formed, either in the remnants of supernovas, and that is also highly debated, whether supernova, type 2 supernova are producer or destroyers of dust, or in the outer layers of AGB stars or older stars. We don't know how the galaxy, how the dust actually evolves. Formation timescales are highly debated. No one really has a clear picture. Mechanisms for formation. So there are now models that imply that the dust is actually formed by accretion on ISM itself. So not in the atmosphere or the outer layers of stars, but in the ISM itself. So the issue, fundamental issue, is that there are many models. There is active research to try to constrain these models. There is no clear picture yet. But many of these high redshift dusty systems fit completely outside all these models. And so there's still a big puzzle.
Thank you.
Okay, thank you. Okay, thank you. Thank you, Daniela. So there are no more questions. If there are more, if anyone has more questions, can write them in the chat and we collect them and then send to the speaker. So thank you, Daniela, again. And we can move to the next speaker. So Massimiliano Lattanzi is already presented. I see here, so we're waiting for you. Okay.
Hello, everybody. Good afternoon. Can you hear me?
Yes, Massimiliano, we can hear you. There's
Okay,
any chance for you to put it in full screen?
Yes, of course. So, okay.
Okay, we can start.
Okay, great. So thanks, first of all, thanks to the organizers for the invitation. It's really a pleasure to be here. It's been a long time since my last meeting organized by all of you, so I'm happy to be here. So topic of my talk is how to probe neutrino physics with cosmological observations. So let's start. So first of all, Yeah. Okay. So first of all, I'll try to convince you that neutrinos are interesting particles to study. So neutrinos are part of the standard model of particle physics, as we all know, but in spite of that, they are puzzling, okay, especially because their properties might be related to physics beyond the standard model. So to make an example, one puzzling property of neutrinos is their mass. I mean, it's the same fact that it's the very fact that they have a mass, because I mean, given the particle content of the standard model, we would expect them to be massless. Even if you introduce a sterile neutrino and try to give them a mass through the usual Higgs mechanism, what is very puzzling is the fact that their masses are so small, as you can see on the left part of the slide, is the fact that their masses are so small with respect to the masses of the other fermions in the standard model. So this might point to a different origin of their mass. So what we still don't know today is the absolute mass scale of neutrinos, even though they know the relative mass differences thanks to oscillation experiments. We don't know the origin of the masses and of the mixing pattern. We don't know the mass hierarchy. So we don't know how the three mass eigenvalues are distributed, whether basically the two that are closest in mass are the ones with the largest mass, which is called normal hierarchy, or the ones with the smaller mass. We don't know whether they are Majorana or Dirac particles, and we don't know whether there is any CP violation related to neutrinos. Now, the point of the talk is that we can use the cosmic neutrino bag, we can use cosmology to constrain the properties of neutrinos, and the reason is that we have a background of relic neutrinos from the Big Bang. This is a prediction of the standard prediction of the cosmological model, and it actually relies on very few assumptions. That means the standard model of particle physics, so the fact that neutrinos interact through weak interactions, and general relativity is applied to a homogeneous and isotropic universe. So once you put these ingredients together, you have that neutrinos are in equilibrium when the temperature of the universe is larger than 1 MeV. Then after that, they decouple from the cosmological plasma and they start to free stream. So they basically don't interact anymore with the cosmological plasma. This means that today we have a background of relic neutrinos with a temperature of 1.9 Kelvin, so slightly colder than the cosmic microwave background, the photons, and a density which is of the same order of magnitude, roughly 100 particles per centimeter cube per neutrino species. So this means that in the standard model, you have only, I should say, 3 free parameters, which are the 3 neutrino masses, even though that's actually 1, as long as cosmological evolution is concerned, since cosmological evolution mostly depends on the neutrino masses. And also, if you factor in the measurements from oscillations, you are left with just 1 free parameter. Now, so this allows you to perform inferences on the mass of neutrinos from cosmological observations, because you have the energy density of neutrinos today, which is just the product of their mass times their number density, only depends on the mass, because the number density is fixed by the arguments that I made before. And then you have that you can write down the density parameter omega of the neutrinos, so their density units of the critical density of the universe, just in terms of their total mass. So here mu is the sum of the masses. So, and I like to say this here at this conference. I mean, I say this every time, but I mean, this is particularly fitting that this allowed Gerstein and Zeldovich already in 1966 to obtain a limit on neutrino masses, because once you require that the universe should not be overclosed by neutrinos, so that omega should be smaller than 1, or not too much larger than 1, then you get a limit on neutrino masses, which is of the order of 100 EVs, which at the time was much better than laboratory limits. Now, things have changed by the name of the game, but the game is still the same in the sense that we basically have limits on omega nu from cosmology, which are of course much better than just saying that omega nu should be smaller than 1, and we translate those limits on the mass. Let me also note that we have from oscillation experiments, given that we measure the mass differences, we also have an estimate of a lower bound for the sum of the masses, which is 60 milli-electron volt in the case of normal ordering, or 100 milli-electron volt in the case of inverted ordering. And this can be translated on a limit on omega nu. Now, how do we know that the cosmic neutrino background is there? So we actually measure the cosmic neutrino background, even though indirectly, I mean, we cannot measure, it's really difficult to measure the neutrinos of the cosmic microwave background because they are very low energy, they are 10⁻⁴ electron volt neutrinos, but we see their indirect effects, their gravitational effects. For example, in the CNB, this is the spectrum of the CNB just multiplied by an additional factor of multiple squared, and you see that the different curves correspond to different amounts of neutrinos as parameterized by this parameter, which is an effective, which is basically the energy density in relativistic species in units of the energy density of a single massless neutrinos with a temperature of 1.9 Kelvin, which is the value that we expect for the standard cosmological history. Now we would expect this number should be 3. It's not actually 3, it's actually slightly larger than that because neutrino decoupling is not instantaneous. This was realized first by Sasha Dolgov in the 90s, and then calculations have been refined especially by groups in Valencia and Naples. And now this is the number that people use at the present, which is 3.046. And so you see that this is in the plot, you see different curves corresponding to the CNB spectra for different values of N effective, and you see that the standard expectation really provides a good fit. You can see that even by eye, the dots, which are the Planck measurements of the cosmic microwave background anisotropic spectrum. Now, so going a little bit in more detail, how do neutrinos affect cosmological observables? So simplifying things a bit, you have two classes of effects. So one are background effects, and these are related to the fact that neutrinos, as all the other components of the cosmological fluid, enter the background evolution. So here you see on the left, you see the Hubble, the Friedmann equation, okay, written by taking into account different components of the universe, matter, radiation, dark energy, possibly curvature, and neutrinos. Neutrinos are quite peculiar because they behave as radiation. They're quite light. So we know from laboratory experiments that the mass of the neutrino should be smaller than EV, more or less. So this means that they behave as radiation at early times and matter at late times. And here in the plot, you can see the equation of state parameter, the variation of the equation of state parameter with time. Okay, so 0.3 is 1/3, so it's radiation on the left, and on the right, and 0 is matter. So you see that neutrinos go from being radiation at early times to being matter at late times. Different curves are for different neutrino masses. So when you put neutrinos, you are changing the background evolution. Okay, so either you are changing the total amount of matter in the universe, or if you want to compensate to have the same amount of matter, you have to compensate either with different curvature or different amount of dark energy or cosmological constant. And this is changing the background evolution. This is something that you see in cosmological observables. To make an example, this is something that you see in the position of the peaks of the CNB. But still, these are effects that can be compensated quite easily, okay, by changing the other parameters that you see in this equation on the left. And then there is another much peculiar effect of neutrinos, which is their effect of the perturbation level, that is due to the fact that neutrinos are very light particles. Okay, so they have large thermal velocities for for most of the history of the universe. So this means that you have a system which is composed by both cold particles like cold dark matter and baryons and neutrinos, which are hot, you have that the density perturbations in the neutrino fluid are suppressed due to collision damping, to Landau damping, which is in the case of cosmological neutrinos is called free streaming. And this reduces basically the peaks in the density field and also slows down structure formation. Okay, and again, this is related by the free streaming length, which is a function of the neutrino mass. And here you can see the effect on the power spectrum. So here, this is the power spectrum of matter as a function of wave number, and normalized to a power spectrum. So it's the difference between a power spectrum with neutrinos, of a universe with neutrinos, and the power spectrum of a universe with massless neutrinos, normalized to the case with massless neutrinos. So you see that at small wave numbers, which is large scales, the two spectra are the same, simply because we are above the free streaming length, so neutrinos behave as cold particles. Okay, but when you go down at small scales, okay, so large wave numbers, you have that there is a suppression of power in the matter power spectrum, and this suppression becomes larger when for larger neutrino masses. The reason being that the larger the neutrino mass, the larger the fraction of matter that is contributed by neutrinos. Okay, and then the suppression effect gets larger. Now, so this is the theory, let's say. No? So what do we observe? Okay, in order to constrain neutrino properties. So first thing is the cosmic microwave background. I'm going fast of this because I'm assuming that most of you are familiar with this. So this is the map of the cosmic microwave background temperature on the left and polarization on the right fluctuations as measured by Planck. So this is a map again of anisotropies. Usually the information in these maps is compressed in power spectra. Now these are actually three maps because the polarization map can be decomposed into two distinct components, which are the E modes and the P modes, which are like the gradient and the curve component of the field, because that's a tensor field on the right. Then you have three fields. So you can take autocorrelation and cross-correlation, so that will make for a total of 6 spectra. Actually, 2 of these 6 spectra are bound to vanish if electromagnetism conserves parity. And then what we're left is with 4 spectra. Planck can measure basically these 4 spectra, which is the autocorrelation of the T of the temperature field, the autocorrelation of the E polarization field, and the cross correlation. And this phi is the so-called lensing potential, to which I will come in a moment. So what is this phi? So the phi field is the lensing potential field, and is related to the fact that when we observe the CNB, we don't see the actual, let's say actual CNB field. When I say actual, we don't see the CNB field that we will see in a perfectly homogeneous universe. Okay, and this is because the CNB photons are propagating in an inhomogeneous universe, and then they are displaced by the gravitational potentials created by the matter that is between us and the last scattering surface. So we have a weak lensing of the CNB, and so the field that we actually observe is the convolution of the unlensed field and the deflection field, what is called the deflection field, which is the graph that you can write as the gradient of a potential. And this potential is in turn related to the line of sight integral of the gravitational potential. So this makes the CNB sensitive to the late time density field. Okay, so this is important because in this way we have a handle from the CNB to the effect that neutrinos have on structure formation. So again, you can extract information from the CNB, and basically you end up going fast on this with a angular power spectrum for the lensing potential, which is shown here on the right. So the other observables that I will be using, that are used to obtain the limits that I'm going to show, are the observations of large-scale structures. So, for example, of the distribution of galaxies, like here on the left, or of the weak lensing of galaxies. Okay, that we also have heard about in previous talks. So these are also very important because on the one hand, they give you the, again, they know about the effect of neutrinos on structure formation, and also because by measuring the baryon acoustic oscillations peak, so baryon acoustic oscillations are basically the oscillations in the baryon fluid that we still see imprinted in the distribution of galaxies, and that can serve as a standard ruler. So measuring the BAO peak that you can see in the plot on the very right allows us to constrain the evolution history of the universe, and this allows us to reduce the possibility, basically, of compensating the background effect of neutrinos that I was telling you about in this slide. Okay, so once you measure the BAOs, you have less freedom into rearranging the parameter in this equation to get the same HOC, basically. Now, so at the end, what do we get? So this is finally the bounds that you can get from CMB alone and from CMB plus BAOs. So I should say that when you use large-scale structures, the first thing that you do is that you use the BAO, because that's a very robust data set. While when it comes to the distribution of galaxies, especially when you're interested in neutrinos, there are some issues that you have to be aware of. One is the bias that we have heard about today, and the other one is nonlinearities, which are important at small scales, which is exactly where the effect of neutrinos is more important. Okay, so here I'm using only BAOs. So this is a typical way of showing these results, which is the mass of the latest neutrino. Okay, the corresponding sum nu, so this assumes the mass difference is measured by oscillation experiments. We have two curves. Red one is for inverted hierarchy, the blue one is for normal hierarchy. And so this is the top horizontal line is the limit from Planck alone, okay, from the legacy release 2018, which is 0.24 eV. And when you add BAO, you see that the limits increase dramatically with a factor of 2 when you get 0.12. What is also interesting here is that you see that this 0.12 really comes close to excluding the inverted hierarchy. Okay, so if you can get below 0.1 with a large enough statistical significance, you are excluding inverted hierarchy simply because in inverted hierarchy the total mass, the sum of the mass, should be larger than 100 millielectron volts. Okay, so these are 95% confidence level limits. Okay, so this is a more detailed summary of the limits that you get from different combination of Planck data and BAO data. So I'm going just flashing this slide. Another interesting thing is that you can constrain the mass hierarchy with cosmology, exactly for the reason that I was explaining a few seconds ago. And so this is the current situation. So here you see the probability as a function of mass, okay, for current data. Okay, sorry?
5 minutes left.
Okay, and if you analyze this data, this is telling you that the normal hierarchy is favored over the inverted hierarchy by current data with odds of 3 to 2. That is basically at the 1 sigma level. Okay, and future data that are shown on the right part of the plot can increase the significance up to basically 10 to 1 if the mass is the minimal mass allowed by normal hierarchy. Now, I still give you a warning here, and that there is a fair amount of model dependency here, because of course we are assuming in making these inferences, this standard cosmological model. Okay, so there is, for example, vanishing curvature, dark energy is just cosmological constant, and so on. So one might be interested in knowing how these limits change when you allow for more extended cosmological models. So this is comes from a study that we made in collaboration with the group of Katherine Freese in Stockholm. And so the first author here was Sanni Magnozzi. And so you see that here, when you, for example, study models with dark energy, with dynamical dark energy, you get that the limit basically gets degraded up to 0.37 eV. Okay. So again, here we have a more detailed table that comes from a review that I wrote together with Martina Gerbino, and you see the limit. So this refers to Planck 2015 data, but just to get an idea. So you start from the limits just for a simple extension of lambda CTM, and then you start adding either curvature or a varying parameter of state, equation of state parameter for dark energy, and you see how the limits get degraded. So now, one thing that I want to stress is that it might be the case that mass bounds actually become tighter in extending models, and this is exactly what happens in this model that was studied by the group in Stockholm again, so by Katherine Freese and collaborators, and especially again Sanni Magnozzi, who was a PhD student in Stockholm at the time. And is that if you take dark energy models, but with a prior on the equation state parameter that W should be larger than -1, so you consider non-phantom dark energy models, you have that the limits on the neutrino mass actually become tighter. Okay, now that I made this disclaimer, let me get back to the limits on the mass and to their usefulness. So this is a recent paper that we made, again, in collaboration with Stockholm and Valencia, and Gordon Kane also in Michigan. And this is the application of these limits, the implication of these limits for particular models of generation of neutrino masses. So I don't want to go too much into the details here, but you can get a model that predicts a form of the mass matrix for neutrinos, and then you can use the limits on the sum of the masses to constrain the parameter of this matrix. Okay, and the interesting thing here is that usually you want this kind of matrix in models of quasi-degenerate neutrinos. So you want this kind of matrix that you see on the left to have to have the parameters that are denoted with delta, delta prime, and so on to be small. And what we see is that cosmology basically excludes this kind of mass matrices, at least with small parameters. Okay. Okay, now let me talk very quickly about the effective number of neutrinos that, as I told you at the beginning, are measured by Planck and are very much consistent with the standard expectation of 3.046, and also consistent with what you measure from standard nucleosynthesis, from Big Bang nucleosynthesis. So there is also a very good agreement between the measurements from Planck and the measurements from the abundances of light elements. Okay, I want to go very quickly on sterile neutrinos. So you can use the phenomenology of sterile neutrinos is very similar to the one of active neutrinos. Okay, and then you can use the data to constrain also the abundance of sterile neutrinos, and in particular you can use them to check whether the sterile neutrino interpretation of the anomalies that have been observed at short baseline experiments is consistent with cosmology, and the short answer is no. Okay, so in the plot on the left, you see the mass of the sterile neutrino versus its coupling on the horizontal axis, and the small black ellipses are the regions where you can fit the anomalies, but then forget about the green region. If you look at the blue region, the blue region is the one allowed by cosmology. So the two things are in strong tension. So what I wanted to say as a very last thing is a very fast, very quick view of future experiments. So we have lots of experiments coming in the near future from satellite and from the ground, both, I mean, for measuring CMB and measuring large-scale structures. So let me start from the SIMONS Observatory. Okay, so I'll go in chronological order. So the SIMONS Observatory is an observatory that will release data, I mean, in the next year. So it's called a 3.5 generation experiment for CMB. So we are just coming out from third generation experiment, and SIMONS is kind of a bridge between third and fourth generation experiments. And you can see the kind of numbers that we can get from different combinations of SIMONS Observatory measurement with measurements of basically large-scale structures. You see, these are very interesting numbers because these will allow to measure neutrino mass, even in the case of the minimal mass allowed by normal hierarchy, not without huge statistical significance, but still, I mean, we will be able to measure the mass at the, let's say, 2 sigma level, more or less, depending on the numbers that you look at. And so S4 is the fourth generation of CMB experiments. So these are experiments from the ground that use hundreds of thousands of detectors in the focal plane, and they are expected to go, when combined with large-scale structure measurements, to the 15 millielectron volt level, okay, which is really impressive and would mean at least a 4 sigma detection of neutrino masses. Another experiment is LIGHTBIRD, which is a space mission. So LIGHTBIRD is actually not measuring directly the small scales that are important for measuring neutrino masses, but it's providing another ingredient, which is a measurement of the optical depth to reionization, which is something that you can only measure, that is very difficult to measure from the ground, and then you need to go either on the stratosphere or in space. And that's because the optical depth to reionization is degenerate, acts like a confusion parameter, let's say, for neutrino masses. So you need to have a good handle. And actually, the numbers that I had shown you before all assume that you will measure tau better than we know now from Planck in the near future. So LIGHTBIRD might provide such a measurement, and again, we combine LIGHTBIRD with CMBS4 and large-scale structure observation, you will get down to the 15 MeV level. So this is my very last slide. I just wanted to tell you that if you want to have the full picture about the future experiments, okay, you can look at this very nice paper by Thijs Brinkman and others. So this is the group of Julien Lesbourg in Aachen. And they did this very detailed study in which they have different combinations of different CMB experiments that you see in the different planets with different probes of structure formation. Okay, and then you see the errors that you are expected to get on the sum of the masses. So these are my conclusions, but I'll let you read them because I think I'm already over time. And let me just thank you for your attention.
Okay, thank you, Massimiliano. So we have 2 questions. One of them you already touched on your presentation. It was made just before you touched that point, and it's from Suesh Shen. How sterile neutrino masses are taken into account? I don't know if you would like, if you want to add something.
Yeah. So I went a little bit quick on this, but so the way in which sterile neutrinos are taken into account. So just let me tell you that this is here we are speaking of light sterile neutrinos. Okay, so it's EV scale or lighter sterile neutrinos. Okay, and you can show that this. I mean, if the sterile neutrino is thermal, okay, has a thermal distribution. Okay, or as a distribution which is a Fermi-Dirac times a suppression factor, that is, and this is what you expect if you produce the sterile neutrino through oscillation from the active one, then basically you can, at the level of cosmological perturbations, you can just recast them as active, as normal neutrinos, as active neutrinos. So what you do here is that you just add one more neutrino, okay? You use the energy density and at the present time and the energy density at early times as parameters in the analysis. And this is basically, as you can see here, a remapping of the mass and temperature of the sterile neutrino. And then you see the effect. And the point is that the effect of a sterile neutrino is more or less the same of an active neutrino. So the idea behind it is the same. In the sense you cannot have too much sterile neutrinos because they would they would suppress structure formation too much. In this plot, you see exactly here. So this is what is called the effective mass, which is a bit confusing because it's not the actual mass of the neutrino. This is an effective, this is the total and effective. So 3 is the normal neutrinos, and the excess is due to the sterile, and the allowed region is basically where you see that you have more dots. So the number of dots is proportional to the probability, okay, in that part of parameter space.
Okay, thank you. There's a second question by Carlos Arguelles. Is there any appreciable suppression of the matter power spectrum when adding standard model neutrinos, which can be constrained by large-scale structure observations? Up to which percentage is suppression at given K?
Okay, definitely the suppression is appreciable, okay, and it's part of the way in which these limits are obtained. So when you factor in also the large-scale structures, so not just the BAO, when you also factor in the matter power spectrum, unfortunately, I don't think I have numbers here. You can make these limits even tighter, and the reason is exactly that the precision of present observation is already enough to constrain the suppression. So some of these limits also go below the 0.10 EV limit. So concerning the number, I think I have the answer in this plot that I shown at the beginning. Yeah, so this is, if you look at the plot on the right, that's exactly the number that you're asking for. So you see that for a mass of, for example, of 100 MeV total mass, so 0.1, the suppression is order 7%. Okay, so you can read the numbers from these at large case. Okay.
Okay.
So you can read the number that you're looking for in this picture.
We can see it. Okay, thank you. There is a last question, but it's related. I think you already showed that also. What is it's by Andrew Beckwith. So what is the status now of sterile neutrinos as a dark matter candidate? Rule it out?
I think that the short question is no. Okay, but it also depends on the production mechanism. But again, those are different neutrinos those are different steriles. It's a different mass range than the one that I'm speaking of. Because if you want to have neutrinos as dark matter candidates, they need to be KeV, because you don't want them to be too hot. So they need to be heavier than EV. And KeV is usually the right mass range. So their status is they are still allowed, even though for some specific production mechanism like Dodson withdrawal, things are becoming difficult, and in the sense that the window is closing.
Yes, but not for others. Okay. Okay, thank you, Massimiliano. I think that we can
Thank you.
Station here because we need to recover some time for the next. So thank you very much. So we can move to the next speaker, is Katherine Freese, who will speak about talks on what dark matter is and what it isn't, and how to find it. So is Katherine ready?
Well, I'm here, but I don't know how to show my slides.
Oh, you will find 4 buttons: the microphone, camera, and share your screen. You don't see it?
I see it, but now it says go to accessibility features in my system preference. Do you know what I do? Oh God.
Oh, Gregory, do we have her presentation? Maybe we can show her slides.
Well, if we can manage to set up the screen sharing would be better. I think we ran through this procedure several times. I would like to ask Gabriele. We still have some minutes. Maybe, Gabriele, can you assist, please, Katharina, to...
Yeah, I'm sorry, when I hit screen, until now it said I didn't have permission from you guys. Now I guess I have permission, but it says go to meeting needs to use accessibility features. But I don't know how to get them. It says go, I'm in security and privacy for the computer, but I don't know but there's a million things in there. So now what?
Okay, I think at this point we would probably need to show your slides and then you can indicate where to change them. Is that okay with you?
Oh my God.
Katharina, don't worry. We'll show the slides for you, and you will just ask us when to change them. Okay?
Well, it's not very good because sometimes I ask to move forward 5 slides. So, yeah. Well,
okay.
Accessibility. I'm in accessibility. I'm in go to meeting, but there's no options. Nothing there. Allow the apps to control to your computer. I hit yes. No, it's not working.
Okay, let's try to project and it will work, don't worry.
Okay.
Just give a comment.
I don't understand. I'm doing exactly what it says to do, but there's... Yep, I can't do it. It's not a lot, nothing's happening. I'm under security and privacy.
Do you see a list, Katie must be speaking, do you see a list of applications? I have to...
Okay, I went to security and privacy. In there is accessibility. In there is GoToMeeting. I click on these things and it just sits there. Nothing happens.
So there is a lock on the...
Ah, there's a lock.
Right?
Oh no, this assumes that I know my password. No, I don't know my password. Oh, Jesus. I was going to use a different laptop, but it went blank at 10 minutes before 11. So I switched laptops in the last minute. And I don't know the password.
So at this point, I think it's better that we show your slides if
Obviously. Yeah, I guess so.
Yes. Okay, Gregory, let's try showing her slides if we can. Okay, here we are.
Let me try one more time. Oh, damn it. Okay, all right, I give up.
So we're projecting your slides now. If you,
yes, I see them. Yes. Okay.
Okay.
Oh boy. Okay. Next slide. So in this slide, I am contrasting the amount of dark matter. So the goal of my talk is to talk about what dark matter is and isn't. So one thing that is still interesting to me is that if you look on the left, you'll see the results from WMAP, which has 23% dark matter, but then the much higher resolution experiment, more sensitive experiment Planck on the right has 26% dark matter, and this discrepancy has not yet been resolved. So I think that's interesting, and we have to figure out what's going on there. Okay, let's go to the next slide. So I have too many things in my outline. Originally, I was going to talk about neutrinos as dark matter, but Massi gave a wonderful talk on neutrinos, so I don't have to do that. So I'm going to just have 2 slides on neutrinos. And then after that, I'm going to go to some new interesting results from LIGO on black holes that other people are also talking about, but in particular, what dark matter might have to do with that. And then on WIMP searches, Donna is still sitting there, and what is going on with that? Dark stars is an idea that we invented about dark matter powering ordinary stars. And finally, there's a new way to test the nature of dark matter. That's the Gaia satellite. And we in particular use stellar streams as a test of cold dark matter. I don't have time for all of this, but let's start with 2 slides on neutrinos. So I want to remind people, this slide here, I don't know if my mouse is visible. Can you let me know? Can you see my mouse? Okay, anyway, you probably cannot. So the amount of neutrino contribution to the total mass density of the universe is given by this equation, which means that within a neutrino mass of 50 eV, you would get a mega neutrino equals 1. However, as we saw from Massi, the sum of neutrino masses is roughly 0.1 eV. It's damn amazing how close we are to knowing the answer. And cosmology is one of the most powerful contributions to that, in addition to the experimental efforts. In the end, neutrinos contribute 0.5% of the mass of the universe, so it's not solving the dark matter problem. So we're going to skip a few slides here. Let's keep going. Continue. This is a stop. Whoops, back up. Okay, so here are some of the many possibilities that we look for dark matter candidates. I'm going to focus on the ones in red are the ones with the best motivation on theoretical grounds, which doesn't make them correct. But I also want to mention, as I'm going along, the work of the young people in my group or formerly in my group. And one of these is Florian Kühne, who has written, go look at his reviews on primordial black holes as dark matter. And he made predictions based on a number of formation mechanisms in the early universe for black holes of various masses. And he actually predicted what I show in the next slide. One of the masses that he found, next slide, please, is the masses that LIGO just found. And I want to point out how unexpected this is, that according to the work of Weaver, Woosley, and Hager, this is the mass of these are the masses of the stellar progenitors. And in this green region, there should be no stars because they would explode by para-instability supernovae and leave no remnants. So then, well, there would be stars, but there would be no black hole remnants. And so you should not see anything in the 50 to 150 solar mass range. And here's to quote Stan Woosley, the prediction is no black holes, not even a few in this mass range. But if we go to the next slide, LIGO has found some, and they are the screen is too small for me to read, but as I'm recalling, 86 and 55 solar masses or something like that. And so, as I mentioned, the predictions of Florian Kühne includes black holes of that mass. And not only that, but I've been working with a student, go to the next slide, please, Josh Ziegler at Texas, and we were looking, what can we do to stop this para-instability supernova with dark matter? And so dark matter heating, if there's a substantial amount of dark matter heating in stars, an example would be dark matter annihilation, then you can avoid the para-instability, and whatever that heat source is, you can fill in that black hole mass gap by preventing the para-instability supernova. This is a draft that he sent me yesterday, and I haven't read it yet. He did all the work by putting into the MESA Stellar Evolution code, which is a nightmarish giant code, this extra heating source, and we have these interesting results. Okay, next page. So I want to turn back to the question of what dark matter is, and there are 2 theoretically well-motivated candidates. That doesn't make them the right ones, as I said. But these are the WIMPs and the axions, which are not invented as dark matter candidates, but instead are byproducts of theoretical work in particle physics to explain other problems. So if we go to the next slide, one of these 2 is axions, the QCD axion. And I want to send you to a review by my former postdoc, Luca Visinelli. And he shows the current status of experiments, axion mass, versus axion coupling to photons. This yellow band is the theoretically interesting band from the point of view of solving the problems in QCD, these kinds of masses. And you can see that experiments are beginning to probe that. And of particular interest is the ADMX experiment, which is taking data and could have very interesting results. So go look at this review by Luca. Let's continue. Next slide. So the favorite candidates for a long time, in addition to axions, have been WIMPs, weakly interacting massive particles. Why are they so well motivated? There are two reasons. One is an amount of them existing today is exactly what you need to solve dark matter problems. Many of them are their own anti-partners. In the early universe, they would annihilate among themselves, and we know how to do calculate things in a thermal bath in the early universe. And we find how many are left over today after the annihilation stops. And this is the answer in this purple slide. And for these thermal WIMPs, you get roughly the correct answer to explain the dark matter that we see today, with the only ingredient in this calculation being a weakly interacting cross-section for the annihilation. And the masses of these particles range from GeV to 10 TeV. Okay, next slide, please. Now, in addition to getting the right relic abundance, WIMPs are interesting because, as I mentioned, they already exist in particle theories in more than one place, but one of the top motivations is supersymmetry. This is an extension of the standard model that attempts to resolve problems of the standard model. And here, every particle we know has a supersymmetric partner. And the supersymmetric partners are mostly unstable in the sense that they decay to lower and lower mass supersymmetric particles until you get to the very lightest one, which cannot decay. And that is the lightest supersymmetric particle is the WIMP candidate for dark matter. Next slide, please. Now, of course, if we want to know if this well-motivated candidate actually is the dark matter in nature, then we have to go detect it. And there's a three-pronged search for the WIMP detection. And it's all three shown in one slide. So if we have the X particles being some candidate for the dark matter, and over here, ordinary dark matter on either side of this diagram, then there are three ways to do the tests. One is going from left to right, the upper arrow pointing to the left. That is collider searches. Another is that if you go in the upward direction, direct detection, or if we go in the right direction, indirect detection. So I'll talk briefly about all three of these attempts to find WIMPs. Go to the next slide, please. The first way to search for WIMPs is making them. So there are attempts at CERN with the Large Hadron Collider, where there is a 17-mile ring with two proton beams accelerated in opposite directions, and they collide at 4 intersection points where there are detectors. If you go to the next slide, when the two protons collide, and there's the attempt to look for supersymmetry coming out of that collision, nothing found as a positive signal, but instead there are bounds such as this one, which is out of date, but the same idea still applies. If I make a simplifying assumption that all the fermions at high mass are unified, all the fermions are unified at high energy, and I make that assumption also that all the bosons are unified at high energy, but then they run to the current masses that we see today. Then you can reduce this 105 parameter space minimal supersymmetric standard model to something manageable and plot everything on one plot. With that very strong simplification, you get this bound where the fermions are on the y-axis and the bosons mass on the x-axis, and you have to be above all those lines in the data. So that looks very constraining, that you have to go to the TeV scale. However, let me go on the next slide to a few comments. If the LHC sees nothing, can supersymmetry survive? And the answer is yes. There are many possibilities. It might just be at a higher scale. So you have to build another detector. it might be a less simple model than unifying all scalars and fermions at some high scale. There's no reason that you don't have to go to more parameters than those 5 simple ones. I also wanted to say that even if you find supersymmetry at the LHC, you still don't know that it's dark matter, because you have to prove that it lasts the age of that there's something that's really out there that lasted a long time. And so you have to do astrophysical searches, as in the next slide. So the idea here is that you take advantage of the fact that there are tons of these things in the galaxy by putting a detector underground made of some nucleus. The WIMP, as in the picture, scatters off of the nucleus, depositing a small amount of energy in the nucleus, and you have to find that energy deposit. Next slide, please. So we were among the first to make calculations for this scattering process. This is on the left, Andre Drukier, me, and David Spergel. So we made calculations for what the scattering would look like for WIMPs in the galaxy. So go to the third slide ahead, please. 1, 2, 1. Keep going, keep going. And these experiments have to be in underground laboratories, such as Xenon in the Grand Sasso Tunnel, because you have to shield from cosmic rays. Next slide, please. So at the time we did this, our numbers showed that you should be able to see something if you had a very sensitive detector, but nobody imagined the sensitivity that you have now in these underground dark matter laboratories worldwide. Next experiment. No, I mean, next experiment. Yes, I'd like that too. Okay, next slide. So of all of these experiments, they all see nothing with one exception, and that is the Dama experiment in the Gran Sasso Tunnel near Rome. We predicted a long time ago that you should see an annual modulation, because the Earth moves around the sun, as shown in this picture on the left. As the Earth moves around the sun, you get a variation in the signal that should give you a peak in June and a minimum in December. And on the right, I show some Dama data going up and down with the time of year, with exactly the right maximum and minimum. And of course, the question is, are these WIMPs or what is it? So next slide, please. So I just wanted to show more. There's more data than what I had on the previous slide. At this point, it's a 12 sigma modulation, and no one knows what it is. Next slide, please. The goal is to find dark matter, and I think we should just skip ahead. And next slide. Okay, and so I have to show this in honor of these very powerful characters in this field. Juan Collier commenting on Rita Bernabai, who was leader of this Dama experiment in the sense of principal investigation, and Eleanor Prele, who's PI of Xenon. And he says, I'm a Spaniard caught between 2 Italian women. So very interesting personalities in this business, and it's a lot of fun. Next slide, please. Now, the problem is that the null results of other experiments are very hard to reconcile with the Dama annual modulation. So here we have a slide of WIMP mass on the x-axis and cross-section on the y-axis for the scattering. The Dama regions are shown in green, and this is an ancient, inaccurate slide, but the idea is still presented, which is that in order to match the null results, for example, of Xenon and Lux, the red and green lines at the bottom, you have to be below those lines. So how is this possible that Dama has not been ruled out? Well, to put everything on one slide, you have to assume spin independent, you have to assume the detailed nature of the scattering, and this bound is assuming spin independent scattering in order to put everything on the same plot, because these are made of different materials. The green Dama regions, we have sodium iodide, and these red and green regions, we have xenon liquid. And so the scattering rate has been assumed to have a certain form in order to put everything on the same plot. And we don't know if that's correct or not. Next slide, please. So these are projections for the future. You can see that we're going to get very, very sensitive, pushing down into this dotted orange region known as the neutrino floor, where neutrinos compete with the dark matter. Next slide, please. I wanted to show in this slide, this is the current recent status of these experiments. And again, this blue region, we're going to get there soon, the neutrino floor, where you have competing signals with the dark matter. Next slide, please. how can you tell the difference between neutrinos and dark matter? Well, for one thing, you know where the neutrinos are coming from the sun and the atmosphere, so you can subtract them off, with the exception of, no, let me continue. So that's number one. Number two, if we have directional detection, if you can determine what direction the WIMPs are coming from, then that really helps. And the third one is a different energy spectrum for the WIMPs versus neutrinos, with some exceptions where you can't, where that's not good enough because the spectra are too similar. Next slide, please. So the good news is that if you really want to make a test of DAMA, you have to have another experiment with the same material, sodium iodide, and that is very actively being pursued. So that's the future of this business. I also wanted to mention a paper that we wrote that looked at the DAMA data only, because they have data down now to 1 keV, where they still see up modulation. However, you can prove just with DAMA by itself that DAMA is not compatible with the spin-independent scattering. It must be some different operator. It doesn't have the right form between 1 and 2 keV to be consistent, the right spectrum. So in the next 5 years, we'll have cosine 100, SABRE, and Anais, also using sodium iodide crystals. Next slide, please. Next slide, please. The most active experiment in this regard is cosine 100, which already had shown this plot in 2019. And so if these are the oscillation fits, and if DAMA is here, then you can see that cosine 100 also has their phase. It looks tentatively like it's in agreement with DAMA, but the statistics are far too low. We have to wait, I don't know, another 4 years or something before cosine has enough data to determine whether or not it's consistent with or rules out DAMA. Next slide, please. So to summarize, we still have this unexplained signal in DAMA, which, you know, if cosine 100 rules out DAMA, then I don't know if we'll ever know what DAMA was seeing. But it is possible that cosine 100 will agree with DAMA, and that would be the most exciting thing of all, and there would be a major discovery. Cosine 100, by the way, is in Korea, a different location. So, and then theorists have to understand what's going on to explain why you see these things in one experiment and not another one of a different material. Is it the nuclear physics? Is it the operator at the fundamental physics level? What is going on? Next slide, please. I mentioned that to go to beyond the neutrino floor, directional capability would really be helped. So if you can tell what direction the WIMP came from, because nuclei typically get kicked forward, then it would be easier to differentiate whether you're seeing WIMPs or something else. Because with the sun is moving around the center of the galaxy, so there is a preferred direction the WIMPs should be coming from. It's the WIMP wind. It's as though we're driving into the rain. So then if you look in that direction, you get 10 times the signal of looking in the opposite. And so I'm mentioning this specifically to show you some ideas that we had in the next slide. So how to get directional detection? Well, we suggested this idea of, this is André Durkier, who went into biology for 20 years, came back saying, let's use DNA. Yes, in principle, it can be done. So if you have here a thin plane of gold, nanometer thin, so 1 atom thin, with a bunch of DNA strands hanging down, then when the WIMP hits the gold, it knocks forward a gold nucleus into these hanging DNA, and the gold nucleus breaks the DNA. You can replicate these broken strands and figure out and do gene sequencing and figure out where did this track happen. So you can figure out the direction, and from that determine what direction the WIMP came from. So George Church, the biologist, he has some pieces of this in his freezer if we get a physicist interested in pursuing it further. Okay, next slide. Another approach that we've worked on recently, in my group, Pat Stengel, Sebastian Baum, Tom Edwards, and the idea is this was done back in the day to look for magnetic monopoles. And also dark matter, the idea of digging up old rocks from 10 kilometers below the surface of the Earth. They've been collecting tracks for 500 million years. And so if you had WIMP tracks due to WIMP decay, then you could find, in principle, find those. And the thing that has changed nowadays is that we have nano tools that can identify nanometer resolution tracks in 3 dimensions and differentiate. The big problem is uranium decay and fission. And so if you can get rid of those backgrounds, then you're good. Next slide, please. Next slide, please. Okay, so then the other approach is to look for search for indirect detection due to the fact that whenever WIMPs find each other, they annihilate, giving rise to a series of decay, giving to a chain of particles ending up typically with neutrinos, gamma rays, and positrons. And so you look for those if you look towards where there's a lot of dark matter, such as the center of the galaxy or in dark dwarf galaxies. Next slide, please. And all 3 of these are being searched for AMS, found in excess of positrons, the Fermi, and Ice Cube. They're all looking for different signals from the dark matter annihilation. Next slide. So AMS found in excess, but I wanted to point to this paper, which was the first to show the following problem. In this plot of cross-section versus mass for some particular annihilation channel, in this case BB bar, if you want to explain AMS, then you've got a problem because the Fermi gamma ray satellite did not see an excess towards dwarfs for the photons that really should accompany any positrons. In the BB bar, you can exactly calculate how many you would get. So you'd have to being below the blue line is not compatible with being in the red circle. Next slide, please. Then there is the thing that's still remaining is a gamma ray axis towards the galactic center. So after they subtracted off backgrounds, there is still at the galactic center an excess of gamma rays, which may or may not be due to dark matter. Very, very hard to tell because there's a lot going on at the galactic center. For example, it could easily be pulsars. Next slide, please. To sum up, there are many ways to go after this problem. Right now, there's the gamma annual modulation signal still there and unexplained. The indirect detection, the Fermi ray, gamma ray excess near the galactic center still unexplained. Next slide, please. That leads me to another approach to look for dark matter, and more interestingly, a new kind of star. Here the idea is, well, let's go to the next slide, please. And the dark stars, we have fans. Just kidding, this movie predated us. Next slide, please. Okay, so the people in the top here, we had this idea. This is Doug Spoliar, Paolo Gondolo and me had the original idea for this. And if you go to the next slide, let me explain the basics of what it is. So the first stars to form in the history of the universe, well, that happened when the universe was 200 million years old, a redshift of, say, 12 to 20. And these things, the only stuff around is hydrogen and helium for making stars. And yes, these are made of hydrogen and helium. However, since they form at the centers of the protogalactic mini halos, at the center, you have a lot of dark matter, and the dark matter annihilation can end up serving as a power source for the hydrogen and helium instead of fusion. And yes, these things shine. They're not dark. We got that wrong. Dark matter constitutes less than 0.1% of the mass of the star. And these things can start out, the dark stars start at 1 solar mass, but can grow up to being 10 million times the mass of the sun and potentially 1 billion times as bright. 2 major consequences. One, you can see them in the upcoming James Webb Space Telescope. And the other is, once they die, they become black holes and could serve as seeds for the giant black holes observed throughout the universe. Next slides, please. I'm going to have to skip a few. I already talked about this. Well, the gas cloud cools and collapses at the center of this mini halo, pulls in more dark matter. The annihilation products include E+, E-, and photons. These things don't get out of the star anymore. They collide, they're trapped inside the cloud, they thermalize with it, they heat it up. So that's the power source, okay? Next slide, please. I've already said this. Next slide, please. And so I mentioned they can be very big. Next slide, please. And when they die, I'm going to skip this. This is their stellar. We did the real stellar evolution for these things, but when they run out of dark matter, then they will collapse and could explain the many large black holes. And of particular interest is the ones at high redshift that are very, very hard to explain any other way. Next slide, please. And so, for example, there's this guy. This is at a redshift of 6, a 10 solar mass black hole. We don't make black holes that big, but if you start with millions of solar mass ones, it's easier to end up with these big ones. There is no solution to this problem. So this is a novel solution we propose. Next slide. And this is a really extreme, a redshift of 7.5, a 800 million solar mass black hole. Next slide, please. And as I mentioned, these objects are detectable in the upcoming JWST. So you see the blue curves are the sensitivity, and the red and other colors are that's the brightness that you could look for of dark stars. Next slide, please. Okay, I also wanted to mention we only did this with WIMPs initially, but now we're doing it with self-interacting dark matter, and it's also going to work. So there's other types of dark matter can also provide heat sources for stars. Next slide, please. To reiterate, many chances of discovery and detection in the next decade. I talked about each of these, so I won't say it again, but let's go on in the next slide to something really new, which is the new ways to test the nature of dark matter using Gaia data. So Gaia is a European satellite that measures positions and velocities of 1 billion stars in the Milky Way. They can figure out how, if you see where things are moving around in the galaxy, that'll tell you, well, this interstellar kinematics is determined by the potential of the dark matter, so you can learn what about the dark matter by looking at how it pulls stars around. Next slide, please. Historically, this is an old subject. Moving from 150 BC to the right, you can see the resolution in arcseconds going from the red dot on the left down to all the way on the lower right. You see Gaia with the incredible resolution that it has for stellar positions and parallaxes. Next slide, please. And so we can test whether cold dark matter predictions are correct or not. Next slide, please. If cold dark matter is right, well, there are some small scale observations that are not quite consistent that we can test using the Gaia data. And in particular, one is this core cusp problem. The upper right diagram shows the density profile at the centers of galaxies and other large objects. So cold dark matter predicts that upper straight line where it says cusp. Now, some observations seem to show instead that there are cores in various types of objects. And the question, if that's true, does that mean that it rules out cold dark matter? So I want to show you another, on the next slide, another way to go after this question, and that is by using stellar streams in the Gaia data. How do streams form? Well, first of all, we know there are 70 observed and new ones constantly being found, and their properties tell us about the dark matter. How do they form? Well, there's two major ways. They can be done by tidal stripping of dwarf galaxies, and the second way is tidal stripping of globular clusters of stars inside halos. And for those who don't know, globular clusters are dense and old star clusters formed at redshifts 2 to 4. I've written this on the bottom. They're about 10 to the 5 solar mass in size and tens of parsecs in physical size. Next slide, please. Here's a picture of the slides, some of the stellar slides in the Milky Way. Next slides, please. And with postdoc Hayati Malhan and Monica Valuri, we went after these guys. So you see a picture on the upper right of, let's say the host galaxies are Milky Way, but we're actually doing simulations. And then you have the smaller subhalo that's being accreted into the Milky Way. Now, inside that host galaxy is a globular cluster shown with the red orbit. Next slide, please. So these are, this is a picture of the simulation of how this happens, the formation of the stream by tidal stripping of this accreted globular cluster. Next slide, please. And what we're finding is they look different. Okay, so inside cuspy halos, you can see that there's a lot of structure here. So you have the basic moral of the story is you have more that this is obviously a wider object, this stream in the upper picture from cuspy halos than in the case of chord subhalos. It's wider, not just physically, but also dynamically. Next slide, please. And so we can actually quantify from simulations what you would expect. And sure enough, the streams coming from cuspy halos are wider physically and dynamically than those from the chord subhalos. Now, the first naive comparison with observed streams indicates a preference for chord subhalos. If that holds up, and I'm not saying it will, then either there is baryonic feedback or we have to go beyond cold dark matter. Next slide, please. And so this is this shows that the baryonic feedback has a Goldilocks sweet spot region for galaxies of about 5 × 10⁻⁻10 solar masses, where this peak is in this diagram. This is again from simulations. Next slide, please. So self-interacting dark matter, for example, can turn cusps into cores. So maybe you're seeing evidence for that. It's either baryonic feedback or new kind of dark matter. Next slide, please. There's also gaps in stellar streams. I don't have to, I'm running out of time. Let's just go next slide to my summary of what you can get from Gaia as far as testing the cold dark matter hypothesis. So the difference between chord and cuspy subhalos produce streams of different widths. So is cold dark matter right? You can tell by looking at that. You can learn from looking at that. And from gaps in streams, you can also learn from those. And I haven't talked about it, but the shape of the Milky Way halo, well, cold dark matter predicts it to be triaxial. You can look for that as well. Gaia also gives you better estimates of the local dark matter density, and the answer is always around 0.3 GeV per cubic centimeter. Next slide, please. So I summarize here. I've gone over, I think, 3 minutes, not too bad. Neutrino mass is getting nailed down by cosmology. That's pretty cool, but it's not the dark matter. WIMP searches, DAMA is still sitting there with a 12 sigma annual modulation signal. It's not spin independent scattering. It's not even compatible with itself. Cosine 100 is testing it. That's exciting. We'll know. Then dark stars, the very first stars in the history of the universe could have been powered by dark matter rather than by fusion. And that could be WIMPs or self-interacting dark matter or who knows what. I also, similar subject, I didn't put it in the summary because it's so new, but so I forgot to add it, but the idea that dark matter heating could stop pair instability supernovae and contribute towards explaining the black hole mass gap seen in the black holes in the mass gap seen by LIGO. That's interesting. And new ways to test the nature of dark matter. Well, the Gaia satellite will help us to learn about the dynamics of the dark matter in the halo. Okay, thank you.
Okay, thank you, Katherine. So for this very interesting talk. So far we have 3 questions. Let me go fast with them. 4 questions actually. We will go out of time. Well, first one out by Andrew Beckwith. What are the constraints on mixing axion dark matter with WIMP dark matter in terms of observational data sets? Also, has warm dark matter ruled out by observational data?
Okay, so it is very possible. I mean, it's very possible that there's more than one type of dark matter. It's already pretty weird that regular matter and dark matter, the baryonic matter and dark matter, they're the same to an order of, well, a factor of 5, right? So we already have 2 types of matter. Maybe there's 3 more. Who knows? So you could have WIMPs and axions, nothing wrong with that. And in which case, all the bounds everybody shows, let's say it's only 10% WIMPs, well, then the bounds are 10% weaker. So that's certainly possible. I hope that answered the question. I'm not remembering it exactly anymore.
Has warm dark matter, is warm dark matter ruled out by observational data?
No, it's not. So that's I was focusing on how to test cold dark matter. Well, if it's not cold dark matter, then it could be warm dark matter. Absolutely. And there are plenty of particle physics models out there that would give you warm dark matter. So that is definitely a viable option. And maybe we'll learn about that, for example, by looking at Gaia data, which tests not one particle versus another, but the nature of cold dark matter, such as do we have cusps or cores in halos?
Right. So next question by Carlos Arguelles. I would like to ask about current tensions for WIMPs and fuzzy dark matter in cosmology.
I'm sorry, say that again?
What about current tensions for WIMPs and fuzzy dark matter in cosmology?
So I think there's you know, I moved to Texas a year ago, and now we've also hired Kim Boddy. She just arrived in Texas, and she did some very interesting work, which is what if here's the funny thing. If the dark matter cross section is not weak, let's say it's with ordinary matter, it's actually on the strong side, then those particles would never get to the underground detectors. So more strongly interacting dark matter, you'd have to do something different. And so what they looked at is CNB data. What would this do to, how would it affect the CNB data? And so they placed bounds on the stronger interacting dark matter. So that I think is very interesting. The other thing is you mentioned fuzzy dark matter. For example, you have ALPS. These are, I showed a plot, which we're not going to go try to find. The review of Luca Visinelli not only looks at the QCD axion, but also axion-like particles. And so these things could have all kinds of different masses, and the bounds that I showed there apply to everything, to all of the possible ALPS of different regimes of mass and cross-section that does not fit into the QCD axion paradigm. There's also light dark matter. There's a lot of work being done on that, and that would be stuff lighter than 100 MeV, which is not going to show up in direct detection experiments. And there's a huge effort to look for that now. A lot of interest for direct materials or superconducting detectors or semiconductors or et cetera, et cetera. So there's a lot of activity of building detectors, but that is for the future.
Okay, thank you. So next question by Alexander Sakharov. What do you think about perspective to explain dark matter using pure gravitational phenomena?
So there's MOND, Modified Newtonian Dynamics, invented by Milgram before my time. And the idea there was that as far as explaining rotation curves of galaxies, the original evidence for dark matter, there are other ways to do it. Namely, you could change Newton's laws as you get out to the larger radii in galaxy. In the case of his model, then it would be as you go to lower accelerations, the force law changes. This phenomenological model was then turned into Lagrangian formulation by Bekenstein and others. And the modern variant of this is Tevis. So I don't think it's very compelling. Then in order for that to work, that stands for what? Tensor vector scalar or something like that. So in order for that to work on all scales, especially CMB needs dark matter. Okay, so if you try to explain everything, I think they'll all agree. You need to have some dark matter. Plus, you have to have these new ingredients of essentially new particles, but in tensor vector scalar in the title. And so, I think it's actually a more complicated model than dark matter. And so, I think you need some dark matter.
Okay, so yes, I would like to finish with a comment. It's very nice to see this model about for the supermassive black holes based on dark matter. I don't know if you will stay for the next talk, but there is a possibility. We have been working in our group for the also explanation of supermassive black holes with dark matter, but from a different perspective, from PV fermionic dark matter. But that would be the next talk.
Oh, you're kidding. Okay, so I got to introduce the material for the next talk. That's great.
Yes, that's right. So we can move to the next talk. So thank you very much, Katherine, for your time.
Thank you very much.
So let's move to the next talk. Is by Carlos Arguelles, Fermionic dark matter profiles. Is Carlos ready?
Yes. Can you hear me?
Yes, but we don't see your screen.
Thank you for making my talk work.
Thank you. Okay, Carlos.
Our
Okay,
pleasure.
we can see now your talk. So please start when you are ready.
Okay, just a minute. I would like to minimize this. Do you know how can I minimize this? I don't know if you see this second window. That is.
We see your presentation. We see your full screen.
Because I have a superimposed a second window with the chat and so forth. I'm trying to minimize.
But that is visible only for you.
Yeah, I know.
Okay, you just can go ahead with your presentation.
Okay. Okay, so thank you, Jorge. Of course, I would like to thank the organizers for giving me the opportunity to present our latest results. Today we'll talk about fermionic dark matter profiles, which is mainly comprised the last nearly decade of work with the group in collaboration with Remo Ruffini, Jorge Rueda, and more recently in the last years with Andreas Ruth and Edward Becerra. Okay, so the outline of the presentation. First, I will talk about self-gravitating fermions as dark matter in galaxies. I will briefly comment about dark matter halo formation in terms of collisionless relaxation. Then I will move to dark matter halos in equilibrium out of self-gravitating fermions and how a novel dense core diluted halo profile arises. Second, I will apply this new profile to the case of the Milky Way and the galaxy center. I will explicitly show how the dark matter fermion core can be an alternative to the black hole paradigm at the galaxy center, and also how the fermionic halo can provide excellent fit to the Milky Way rotation curve. Finally, I will mention all the universality of these fermionic profiles from dwarfs to elliptical to galaxy clusters, and briefly comment about the possibility to provide a paradigm shift in the formation and nature of our galactic centers. Okay, so let's start with the dark matter halo formation in terms of collisionless relaxation. We would think dark matter in the beginning as a collisionless particle system described by mean-field Blasov-Poisson equation. So this equation you see here on the left, which is in this case is coupled to gravity. See this Poisson equation. The F is of course linked with the minus gradient of gravitational potential, and M is the mass density of particles in terms of the integral of the pool phase space distribution function, which also depends on time. The main step here is to this Blasov equation can be rewritten in a different form for a coarse-grained F-bar distribution function, making two steps. First, decompose the initial distribution function into a coarse-grained plus fine-grained fluctuations, and then take local average. So by making this, you can get to Blasov-Poisson into this new equation, but for the coarse-grained. When in the right hand side, you have a current, a derivative of a current, the so-called diffusion current. This equation generally has the name of a convection diffusion equation, which the current has the information of the fine-grained fluctuation average. So the challenge here is to solve this equation in order to try to find a most likely obtain the current, which is the complicated one. But interestingly, there is this so-called maximum entropy production principle, which has been developed and applied to this by Chavani in this work, where you can constrain the you ask the current to fulfill macroscopic constraint, meaning first law of thermodynamics and second law of at coarse-grained level, meaning E dot equals 0 and S dot larger equals 0. So the key assumption here is that during its evolution, the system maximizes its rate of entropy creation while satisfying the constraint for independent dynamics. Therefore, applying this maximum entropy production principle plus quasi-linear theory was developed in the 80s, the equation 1, so this one here, can be rewritten in a modified Landau equation. This one here you see on the left, which for the case of stationarity, so when entropy has been already maximized, so you have no time dependence now, allows you to obtain the current, and for an assumption of current equal constant, you can have finally a solution, a stationary solution for the coarse-grained phase space density at relaxation, which this MEPP principle provides you a Fermi-Dirac-like distribution function, a relaxation, that you see here. And interestingly, this generalizes the Linden-Bell distribution function from violent relaxation. Indeed, this is you can obtain the standard Fermi-Dirac-like Linden-Bell function by taking J equals 0. When no diffusion is taken, you obtain the standard. Okay. Interestingly, of course, as you know, Linden-Bell theory of violent relaxation was developed by classical, was meant to be by classical particles, right? He claimed indeed that has found the fourth statistics, right? A Fermi-Dirac for classical particles. Then the Linden-Bell's violent relaxation mechanism was extended also to indistinguishable particles, in Krul et al. 2 decades later, for example, for neutrinos. And in that case, the maximum accessible value of the distribution function is given by the quantum, right? The h cubed here, a Pauli principle. You cannot have more than one access state in a microcell. And this maximum value here from Pauli principle differs from the one traditionally or originally provided by Linden-Bell, because in Linden-Bell, this maximum or effective exclusion principle was given by the incompressibility of the Blass-Boson equation, the UBO, right? Okay, so we will then work with this Fermi-Dirac-like distribution function and try to build an equilibrium dark matter halo out of this underlying distribution function. So let's consider fermions under self-gravity. First important point is that they do admit a perfect fluid approximation. This was demonstrated in this original nice work of Rufino Bolassola in the 69 by solving Einstein-Dirac equations. Indeed, for example, it doesn't work for bosons, because bosons condensate and cannot have without any further interaction, cannot have a perfect fluid approximation. So we take, therefore, we try to solve, this is our work now, solve Einstein equation for semi-degenerate gas fermions in hydrostatic equilibrium. So you see the equations here on the left. So the first two are Einstein equation, spherical symmetry, mass equation in GOV, or perfect fluid. Third equation is Klein condition, so first law of thermodynamics for equilibrium structure. Fourth is Tolman isothermality, so the isothermality condition, and fifth is energy conservation along geodesics for the particles. Okay, the source of these equations, coupled systems equation we try to solve, are density and pressure here, which are written in terms of which I told you, the Fermi-Dirac-like distribution function with a cutoff in the energy, the numerator. This cutoff implies that for energy larger than the cutoff energy, you have this numerator is equal 0, and then you have no particles. So particles have already escaped. And for energy below, you have this distribution function. Therefore, this is a coupled system. You have the equation of state in terms of the porcelain Fermi-Dirac distribution function of relaxation. And you have this theory have 4 free parameters. You can see on the bottom right: mass, temperature parameter, degeneracy parameter, and cutoff parameter. Important here is that you have to solve the boundary condition problem. This is, as you know, ordinary coupled system with integral differential equation. You have to solve the boundary condition problem. The key point is that the mass is not singular at the origin; it's regular, that will start from 0. And other very important point is that the degeneracy parameter, theta 0, will be taken larger than 0, meaning that you want solutions to be degenerate at the center or semi-degenerate at the center. And we will not be interested in diluted solution. For, as you remember, when the degeneracy is lower than -1, the Fermi-Dirac tends to Boltzmann. So you will obtain the famous skin profiles, but this is already known story, so we will pay attention to the central degeneracy. So the most general solution out of this equation is for the density, you see here, density against radii, is this continuous curve, which on the right-hand side, this has been solved, for boundary condition typical of spiral galaxies, so tens of kiloparsec here. And at these scales are very similar, the solution to the NFW and Court in ASTO, where data is more available. But through the center, and given the Pauli principle, the semi-general fermions are support against gravity by generalizing pressure. And you see here the core, a highly dense core. Importantly, all our solutions has fulfilled the quantum condition, meaning that the de Broglie wavelength of the particles are always larger than the particle mean distance at the core. And this always happens for the generously larger than 10. Another very important point is that the dark matter profile depends on the particle mass, and I will explain better this point. So the important point here is we have a new core halo profile, which in the halo part is similar to the ones in the literature, but in the center has a degenerate core, which we would like to know which is the meaning of this core when compared with observations. So now let's apply to the case of the Milky Way. So let's start fast with the main observables of the Milky Way. So we have, as you remember, the central parsec is governed by a dark compact object of 4 million solar masses. The central kiloparsec is governed by an inner and main spheroidal bulge. The central tens kiloparsec governed by a flat disk, and the outer region is governed by a spherical dark matter halo with these values. Probably some important point. In the bottom right, you see the famous rotation curve, nearly flat. At this is linear scale. But interesting is the bottom left of the rotation curve is in logarithmic. That is why you see this bit weird shape of the rotation curve. But it's important this point because Sofue, which is the expert of observation and rotation curves, has shown was able to link the inner parsec here, the inner gas of particles here, with the total outer rotation curve going through the main bulge. So, of course, as you know, the central part of the galaxy has bars and streaming motions, not completely tangential, of course, but he provides an effective rotation curve where the error bars accounts for this streaming motion. But interesting is that he, for the first time, linked the Keplerian trend of the rotation curve outside the central object with the first gas motions at the 1 parsec distance. So you have a full rotation curve. So, of course, but we can, let's go a bit deeper inside the central of the galaxy. So let's go to the milliparsec up to the 1 parsec. We know, of course, there's a lot of activity and for baryonic matter, but about the dynamics, it consists of young stars and molecular gas, which obey a Keplerian law, proportional to R to the -1/2. And this observation was thanks to the near infrared techniques developed by this work of Gillesen. And probably to say the most important objects are S2 star, which is one of the nearest around the galactic center, and the She2 cloud, which is a flyby. It's not complete orbit, but it's also quite nearby. The important is that the S2 star is the one which better constrains the central mass object, about 4.2 × 10⁶ solar masses, within a radius of a milliparsec approximately. So the objective here is to see if our core halo profile, this novel core halo profile of fermions, can explain the dynamics of these stars. Let's move to the next slide. So here is the main question which motivates all of our work. Can the overall gravitational potential of this core halo profile explain the Milky Way rotation curve as well as the S-star dynamics without the central black hole? Okay, in order to answer this, we have to solve the former boundary condition problem and to see if there is a set of 3 parameters that allow to fulfill that the core dark matter core mass reproduce the 4.2 × 10⁶ solar masses, and also 2 other very well constrained values for the mass at 20 kiloparsec by Sofue and at 40 kiloparsec by the experts Gibbons Belocruz of constraint from Sagittarius dwarf satellite. Okay, so the answer is yes. We have indeed, it's not only one solution, we have a family of solutions. This work was published in 2018. Was a family of solutions. You can see in the plot of the left, a family of density profiles, again with the central semi-degenerate core at the center. And here is explicit the mass dependency of the profiles. You can see, for example, for sub-keV dark matter, the core, because the relation is the larger the particle mass, the more compact is the core of the dark matter. Therefore, for 0.6, the core is too extended. You can see here, and then you can compare the corresponding rotation curve that the maximum, the first maximum rotation exceeds the rotation curve, so this is excluded. But there is a range of particles between 48 keV and 340 keV, the black, between black and gray, dash gray, which can, when you see the picture on the right, fulfill with the overall rotation curve data, and also explain, this is the first blue star here is S2, these are the other 7 best constrained stars. So this solution can provide can fit the average circular velocity of these stars following a Keplerian desired trend here, but also all the rotation curve from inner bulge and to outer bulge. Well, of course, you see that in the intermediate range, the domination is bulge and disk. Dark matter is only important below the 1 parsec, and then above several kiloparsec when it is needed to explain the flatness of the rotation. So, conclusion of this, we have a range of particle masses between 48 and 300. You may wonder why 300 is the maximum. It's because above this value, the central core reached the critical mass for gravitational collapse. This is analogous to the Chandrasekhar mass, but for these neutral fermions. And then you have this family of profiles. I would like to show also a zoom to the halo. This is in linear scale. When you compare explicitly with NFW, in black you have full NFW with baryons, and in red we have a rare profile with baryons. So both can provide a very good fit to the range in which the rotation curve is better constrained. You see, of course, after 30 kiloparsec, the error bars systematically are too large, and therefore are comparable both models regarding the fit to the rotation curve. But probably the most interesting part of this work is which was recently appeared in ANA this month, is to try to explain, because any alternative model to the central black hole scenario must explain the detail, the full, very high precision data of VLT, Keck, Gemini North Subaru telescope, with, for example, these 3 data sets, right? The multi-year accurate astrometric data of S2, including, as you know, probably the news of the relativistic redshift, the corroboration of the relativistic redshift of S2 around the center. This is the, and also the people from Germany of Guess et al. Also, the currently available data on the orbit and redshift of G2, the cloud, and very interesting also the G2 post-pericenter passage deceleration, which was observed, which in order to explain this deceleration after pericenter in the black hole scenario, you need to invoke a drag force. Okay, therefore, we were wondering, can our degenerate core at the center explain all these 3 data sets comparable or even better than the black hole scenario? Well, I will show this in detail. So first, let's show the theoretical in this plot on the left. You can see the S2 orbit, y-axis right ascension and declination. You see the dots, the gray dots are the data collected by the past 26 years by all these 4 biggest telescopes on Earth. And in red, you have the theoretical prediction of our model, and in blue, you have the black hole. So you can see, and here you can see the residual, so you can see that both can comparably explain the positions of the S2. You can see here a bit better, the chi-square is a bit lower for the case of our model, but are on equal footing, you can say. Okay, sorry. Then let's move to the observed line of sight radial velocity, or so-called RESI function S2. This is when it's approaching, which is preceding, and of course, as the period of S2 is 16 years, and the observation are along 26. So we have more than one complete orbit. Again, both models can produce analogous chi-square to fit this data. And here to the right, I also wanted to add this nice plot. In the bottom, you can see the blue, the black hole, the redshift excess, right? So here in the dashed gray, you see that there is no no excess due to just Keplerian motion of the star, right? But the data shows really an excess. It means that there is a relativistic, relativistic terms or contributions to this redshift that the black hole can fit very well, but also our model can fit with similar chi-square. So redshift relativistic excess can be fit by both models. Probably the most interesting, or probably no, indeed the most interesting case is the G2 cloud, because the orbit here, you can see the data with the gray dots, and both models, rare and black hole, can provide similar identical chi-square here because they're very similar regarding the position of this orbit. For the best fit for the mass black hole is 407 × 10⁶. In order to provide this fit, and for our dark matter core is nearly 3.5 × 10⁶ for a particle mass of 56 kilo-electron-volt, the same as S2. But the key point comes when trying to fit the line of sight radial velocity. As I told you, there is a observed deceleration. You see these gray dots after post-phase center passage. And the blue dashed curve corresponds to black hole. We cannot fit this data after phase center passage unless you invoke a drag force by an accretion flow. So we were wondering, can some dark matter core of fermions can explain this data for the same particle mass that for S2? So incredibly, we found a possible solution for this for 50 keV, where you can see the difference of chi-squares. In our model, we are below 1, while in the black hole, the discrepancy is quite much more higher than chi-square. So this is very interesting because for a unique mass of 50 keV, we can provide a good alternative to the black hole compared with all the available data until today for S2 and G2, and also provide a good fit to the Milky Way rotation. Okay, these profiles not only apply to the Milky Way, but are universal. We have published last year and applied to dwarfs, spiral, and ellipticals. This is a family of available profiles able to fit specific data constrained by observation. For example, in dwarf, we took the 8 best result Milky Way satellites with these values at inner halo scales. Also a sample of nearby this galaxy from things from which we had to fit these halo boundary conditions, and in elliptical we took some galaxy samples by glancing. So
5 minutes left.
Okay. So here is to say that by making a full coverage with the free parameters of our model, and for particle mass always 50 keV, we can have a family of solutions able to fulfill this data, this halo data provided by observations, and provide a family of possible cores. So this is a prediction. For example, in the case of spirals, let's look for a moment here in the mass. You can see that this is the core mass. This plateau corresponds to the core mass. For example, in the case of galaxies, they go between 10 to 5 up to 10 to 8 solar masses for the dense dark matter core. And interestingly, in dwarf, they go from 10 to 3 up to 10 to 6. Therefore, here this is suggesting that the central cores in dwarf may provide an alternative to intermediate massive black holes, which is not known the nature yet. And in spirals and elliptical can provide an alternative to supermassive black holes up to 10 to 8 solar masses. Indeed, we have tested this as this prediction that the central core, so I repeat, provide alternative either to intermediate massive black holes up to supermassive black holes, for example, in active galaxies, some safer or ellipticals. And in this picture here, you can see the shaded green area, which is the full prediction for model regarding total halo mass and dense central core mass in comparison with the black hole. Right here is this relation was found by Ferrarese. I mean, the green is our prediction, but the correlation found by Ferrarese is the strip, this light blue strip. That this is not the famous M sigma relation, but it's another relation she found which correlates the core mass with the total halo mass, so all dark. Therefore, we were able to show that there is always possible to find a set of parameters, these points A, B, C, and D along the correlation, in which you can be inside the correlation for each kind of galaxies, from average galaxies to ellipticals. Okay, an interesting point here, which is related with Katherine's comment about how you can provide an alternative picture for supermassive black hole seed, is that the degeneracy pressure supported by these cores can become gravitationally unstable, reaching the critical mass and collapse. This, for 50 keV, you have a critical mass of collapse of 2 times 10 to 8 solar masses. So this is what is interesting, because you can think that at formation, you may think at high redshift, this binary relaxation generates this core halo structure, which in some cases the core is critical, collapse to a supermassive black hole 10 times 8, and provide the seeds for subsequent accretion to form supermassive black hole of 10 to 9, 10 to 10, for example, as the recently observed M87, which otherwise will be difficult to explain with normal seeds, because you will need above super Eddington accretion rates. Okay, finally, therefore, we have this suggestion that if these kind of core halo models are a reality, then it is interesting to think that for normal galaxies, here on the left, that does not show an active nuclear nor sheds, may hold a degenerate core of dark matter at the center and not a black hole. While for active galaxies that do have shed emission and hard X-ray, etc., they do need a black hole, which may be the seed, the collapse of this black hole seed. So this may be this dichotomy, which is interesting to think. Okay, finally we move to conclusions. Two main conclusions. The main mechanism behind dark matter halo formation is collisionless binary relaxation, which leads to a most likely coarse-grained distribution function, which is of Fermi-Dirac type and can lead to core halo relaxed structures. Open questions here. Some open questions is why nature will select this core halo in front of Boltzmannian ones, which are similar to series of thermals. Well, some answers can be given by thermodynamical stability analysis, because there are some work showing that core halo structure are more likely to arise than simply dilute, because they are more long-lived and likely to form the conditions to arise. But this is open questions. Then, how is this? What about incomplete binary relaxation? We know that binary relaxation of inner belt is very nice, but it's incomplete in the sense that the time scale are so fast that the part that relax mainly are the central parts, but the outer parts are not fully relaxed. So, but this is will only modify the halo tails, but not the right central physics, which is the more important key point of our work for the degenerate cores. So this is no problem. They will much shift in the tails. Well, and the other main conclusion is that core halo system of 50 keV fermions can explain galaxy rotation curves while providing an alternative to the central black hole in Sagittarius A, but also provide dark matter seeds for 10 to 9, 10 to 10 supermassive black hole formation. Open question here is, which is the nature of these 50 keV fermions, which are predicted only by galaxy data? well, there are some hints for example, maybe possible right-handed neutrinos with some dark sector interaction. These are recent work we have done that fit this data, but there are also other options. For example, some works from some options for dilute STERILE neutrinos. There are some other options. This is an open question, very interesting indeed, which is the nature of this. This is nearly 1/9 of the electron mass. There are new physics here to be explored. Probably, as Katherine also said in the last talk, is that direct detection, there is not yet the sensitivity to test warm dark matter of these scales, but probably in the future with new materials, it can be proven this mass range. And finally, well, this what about the shadow of the black holes, right? Because in our case, the dense core will not cast a shadow because it's not singular. And we have shown that for strong lensing, it will cast Einstein rings. So this will be also interesting with for future higher precision observation in one galactic center. We can distinguish between these two scenarios. Thank you very much.
Okay, thank you, Carlos, for the presentation. There are two questions. First one by Ivan Siutsu. Have you taken into account the gravity of ordinary baryonic matter in the calculations of dark matter profiles for our galaxy? The profiles should be changed at the outer parts, as there is a middle range part dominated by baryons.
Well, thank you. Well, in this work, let me show this slide. Go back to this one. Yeah, for example, this one. We have calculated the underlying, only solve for the underlying dark matter distribution, and then using the relation that square velocity of dark matter is total is equal to the square velocity of dark matter plus baryons. We add baryons on top of the dark matter, and then you obtain this fitting. Then if you ask if we have solved in the dark matter plus baryons self-gravitating in the same equations, we do not. We are working on this, but mainly regarding how baryonic matter may fall inside the central core. But this is that may, of course, provide a feedback in the profile of dark matter, slight feedback around the center. But this is work to come. But important is that only for dark matter only solution, you can provide very good fit to data. This is the important point now.
Okay, and last question is by Alexander Zakharov. So did you try to fit observational data, namely trajectories for other bright stars, in addition to S2 and G2, with your dark matter model distribution instead of the conventional black hole at the galactic center? What about your prediction for the shadows at the galactic center and M87?
Yes, very good questions. Thank you. Yes, well, we are starting to now, because this was very recent results about S2 and G2, but we are now starting with some students, for example, that I have here in Argentina. Also, we'll be collaborating with our ICRANet group. And yes, we are starting to study new stars. Not any result, yes, we are starting. And regarding the black hole shadow, well, as I told you, we have in this work here, in this work here, PRD 2016, we have analyzed strong lensing predictions of these degenerate cores at the center, and they cast Einstein rings instead of black hole shadows. So similar, a bright ring of light, which has some similar features than a shadow, but of course it's different because intensity is different. And well, regarding M87, we cannot say. I mean, our picture is consistent with that because we are saying that 10 to 9 solar mass black hole will, in our picture, will be formed from the seed of 10 to 8, and then well, I mean, our model only this dense force only work up to 10 to 8 for a mass, right? So for M87, you have to assume that the core collapsed towards a black hole, and then you, of course, you will have a shock.
Okay, thank you for your answers. So I think we can conclude the session. So I would like to thank you all for your contributions, for your attention, and for the patience that you have with this delay, half-an-hour delay. We had a few technical problems, but I think it's at the end this session was wonderful. And so thank you all, and see you tomorrow.